Picture this for a second. 10 devices. All identical. All silent. No fuel lines. No batteries being swapped. No external power source in sight. And yet, when they were linked together, something happened that nobody in the room was prepared for. This is the moment that has divided engineers, shocked observers, and reignited one of the most controversial debates in modern energy history. For years, the Maxwell MSED device has sat at the edge of mainstream attention. Supporters call it revolutionary. Critics call it impossible. Most people have never seen one operating in a real-world setup. Until now. Because this time, the experiment wasn't about running a single unit in isolation. It was about scale. 10 Maxwell MSED devices were brought into a controlled environment. No dramatic lighting. No marketing show. Just a simple objective. Connect them, synchronize them, and observe what actually happens when theory meets reality. At first, nothing felt unusual. Each unit behaved exactly as expected on its own. Stable readings. Normal output ranges. Skeptics in the room relaxed, almost bored. This was supposed to fail. That's what the equation said. That's what decades of conventional engineering insisted. Then the linking process began. One by one, the devices were connected into a single network. As the 10th unit came online, something subtle changed. The system didn't just add power, it stabilized. Fluctuations smoothed out. Output curves that normally wavered began to flatten into something unexpectedly consistent. That's when the room went quiet. Engineers leaned closer to the monitors. Independent observers started double-checking measurement tools. No one spoke, because everyone knew what they were seeing shouldn't be happening this way. The combined output wasn't behaving like 10 separate devices. It was acting like a unified system, more efficient, more stable, and oddly scalable. And here's where everything shifted. As load was gradually increased, the expected drop never came. Instead, the system compensated. Automatically. No external adjustment. No human input. The network adapted in real time, redistributing internal dynamics in a way that conventional systems simply don't. Some called it emergent behavior. Others called it measurement error. So the test was paused. Instruments were recalibrated. Power sources were inspected. Nothing changed. When the system was restarted, the same behavior appeared again. This is the moment that split the room in two. On one side were those who said, "This demands deeper investigation." On the other were those who said, "This challenges first principles, and therefore must be wrong." But history has seen this standoff before. Every disruptive leap faces the same reaction, not silence, but resistance. What made this test different wasn't a bold claim or a viral headline. It was repeatability. The same linking process. The same stabilization. The same unexplained efficiency pattern. Again and again. And that raised a much bigger question. If 10 devices behave like this, what happens at 50? 100? 1,000? What happens when systems stop acting like isolated machines and start behaving like coordinated networks? Suddenly, the conversation moved beyond one inventor, one device, or one experiment. It became about the future of energy itself. About whether our current models are incomplete. About whether something we've dismissed as impossible is simply unexplored. Because the real shock wasn't what the system produced. The shock was what it refused to do. It refused to collapse under load. It refused to behave like conventional systems. And it refused to fit neatly into existing explanations. And this is where the story is just beginning. Independent meters were brought in. Thermal cameras. Oscilloscopes. Load banks calibrated to industrial standards. The kind of equipment used not for demonstrations but for debunking. If this system was going to fail, this was where it would happen. Yet the more they tested, the stranger the behavior appeared. Heat signatures remained unusually low. Losses that should have increased with scale didn't rise proportionally. Instead of straining under demand, the network seemed to settle into a more efficient operating window, as if the act of linking created a new internal balance that a single unit could never reach alone. At this point, even the most vocal skeptics stopped laughing. Because the failure mode everyone expected never arrived. One engineer quietly pointed out something unsettling. The system was not amplifying power, it was managing it in a way that reduced waste beyond conventional expectations. That distinction mattered. If true, this wasn't a violation of physics. It was a challenge to how energy flow was being interpreted inside closed systems. And that's where the conversation took a deeper turn. The Maxwell MSED network wasn't behaving like a generator. It was behaving more like an organizer, drawing from multiple micro-interactions, synchronizing them, and minimizing destructive interference. In simpler terms, it wasn't creating energy out of nothing. It was refusing to lose as much as it should. That realization made the room uneasy. Because if efficiency could increase with scale instead of decrease, entire assumptions in power engineering would need revision. From grid design to transportation to manufacturing, everything would have to be reconsidered. At this stage, no grand announcements were made. No press release. No victory speeches. Just a decision. The tests would continue. Different configurations were attempted.
Devices were swapped.
Cabling was rearranged. Loads were randomized. Each time, the behavior persisted. Not identical, but consistently anomalous enough to demand attention. Then came the moment nobody expected. When two devices were intentionally removed mid-operation, the remaining system didn't collapse. It adapted. Output dipped briefly, then stabilized again, like a living network compensating for damage. And that's when someone asked the question no one wanted to say out loud. What happens if this is real? Because if it is, the implications are enormous. It means distributed systems could outperform centralized ones. It means energy infrastructure might not need to grow bigger, just smarter. It means mobility, aviation, and remote regions could operate without dependence on massive external supply chains. But it also means something else. It means the resistance won't come from disbelief anymore. It will come from disruption. Industries don't fear impossibility. They fear replacement. And the moment a technology suggests a different path, one that reduces dependence, cost, and control, it stops being a curiosity and becomes a threat. And right now, this network of 10 quiet devices is sitting in a lab, doing something no one can fully explain yet. Not loudly. Not dramatically. Just consistently. Word spreads fast in technical circles, not through headlines, but through whispers. A call here. A late-night message there. Within days, people who had no connection to the original test were asking very specific questions. Not, is it real? But, what configuration were you running? And how did the system respond under asymmetric load? That's when the experiment quietly changed phases. The next setup wasn't about confirmation.
It was about stress.
Uneven loads were applied deliberately. One side of the network was pushed harder than the others. In conventional systems, that's where instabilities show up, oscillations, overheating, cascading failure. Everyone expected a breaking point. Instead, the network shifted internally. No alarms. No spikes. Just a redistribution that looked intentional, almost optimized, as if the system preferred imbalance because it revealed something fundamental about how energy was moving inside the loop. By now, nobody was calling it a coincidence. One observer noted something deeply uncomfortable. The system's behavior resembled principles seen in complex adaptive systems, grids, biological networks, even swarm dynamics. The devices weren't thinking, obviously. But together, they were behaving in a way that individual components never could. And that's dangerous territory for established theory. Because engineering is built on predictability. This was consistency without full predictability. A narrow boundary where results stayed repeatable, but explanations lagged behind. Requests started coming in quietly for demonstrations elsewhere. Different environments. Different oversight. Different power standards. Not endorsements, not approvals. Just observation. And still, no public announcement.
Why?
Because once you claim something like this, you can't walk it back. If it fails publicly, it's finished. If it works publicly, it stops belonging to its creators. Control shifts immediately to regulators, corporations, governments. Someone in the room said it plainly. The first mistake would be going viral. So instead, the system was documented. Every cable, every timestamp, every anomaly logged. The goal wasn't to convince the internet. It was to survive scrutiny from people who actually know how systems fail. Then something subtle, but critical, was noticed during long-duration runs. Over time, performance didn't degrade. There was no creeping inefficiency, no gradual thermal buildup. The metrics everyone expected to drift didn't. Hours turned into extended cycles, and the system behaved as if time itself wasn't stressing it the way it normally would. That's when the narrative quietly shifted again. This was no longer about output. It was about sustainability of operation. If a network can hold stability indefinitely under dynamic conditions, that changes design philosophy entirely. You stop planning for decay. You start planning for longevity. And that's when external interest stopped being academic. Because a system that doesn't rely on continuous external input, doesn't suffer cascading degradation, and improves behavior when scaled, isn't just an energy question. It's a strategic one. At this stage, the original experiment with 10 devices had already done its job. It wasn't proof. It was provocation. It had forced the right question into the open. Not does this break physics? But what have we been missing? And the next round of testing, already being discussed behind closed doors, won't be about 10 devices at all. It will be about whether this behavior survives contact with the real world. Because labs forgive mistakes. Reality doesn't. No press briefings. No demo videos. Just movement, quiet, deliberate movement. The devices were relocated, not far but far enough. Different facility. Different power environment. Different observers. Same question. Would the behavior survive outside its original context? Because if this effect depended on a specific setup, it would fade the moment conditions changed. That was the hope of the skeptics. Controlled anomalies happen all the time. Real breakthroughs survive migration. So the system was rebuilt from scratch. Different cabling, different grounding, independent loads supplied by equipment that had never been anywhere near the original test. Every variable that could be changed without altering the devices themselves was changed. And still, there it was. The same stabilization. The same refusal to spiral under stress. The same quiet efficiency that didn't announce itself, but persisted stubbornly. At this point, one of the observers finally voiced what everyone else was avoiding. This isn't a device problem anymore. It's a model problem. Because models predict failure modes. Models predict saturation. Models predict loss curves. And none of those predictions were lining up cleanly with what was being observed. Not wildly wrong. Just wrong enough. That's the most dangerous kind of contradiction. Then came an experiment that wasn't planned. A brief interruption, less than a second, cut through part of the network.
Not a shutdown.
Just a transient disturbance. In most systems, that's enough to cause desynchronization or, at the very least, measurable instability. Instead, the network resynced. Automatically. Silently. Without overshoot. That moment changed the tone entirely. Because resilience isn't about peak performance. It's about recovery. And recovery like that usually requires layers of control systems, software, sensors, feedback loops. None of those were present. Whatever coordination was happening, it was inherent to the way the devices interacted when linked. And this is where the story stops being about 10 units. Because from an engineering standpoint, 10 is trivial.
10 is a test.
10 is a warning. 10 is what you do before deciding whether something scales or whether it breaks spectacularly when pushed. And the people watching knew exactly what question was coming next, even if no one said it out loud. What happens when this isn't a network in a room, but a network across distances? What happens when linking isn't done with short cables, but extended lines? Different loads, different environments, different failure points. What happens when the network can't be babysat? Because if the behavior seen here is real, repeatable, resilient, indifferent to configuration changes, then the limit isn't technology. It's courage. The courage to test it where outcomes can't be quietly contained. And somewhere between the blinking LEDs and the unreadable calm of the monitors, a realization began to settle in. The experiment didn't need 10 devices anymore. It needed a reason not to try more. Because the moment you move past 10, you cross an invisible line. Beyond that point, you're no longer proving a concept, you're testing consequences. More devices don't just increase scale, they increase exposure. More eyes. More risk. More pressure for explanations that may not exist yet. Still, preparation began quietly. Not for a public expansion, but for a conditional one. The kind designed to fail safely if failure was even an option anymore. Simulations were run, though most of them contradicted what had already been observed. The models kept insisting on instability at higher counts. The real system kept refusing to comply. That gap became impossible to ignore. One analyst pointed out something subtle but profound. The network didn't seem to care about quantity as much as coherence. When the devices were linked properly, numbers mattered less than alignment. Poor alignment created inefficiency. Better alignment created stability, which raised another unsettling possibility. What if earlier failures, past experiments dismissed or forgotten, weren't failures at all? What if they were misaligned attempts, abandoned before coherence could emerge? That thought changed everything, because it suggested the technology might have been misunderstood from the start. Evaluated as a standalone machine instead of what it actually wanted to be, a participant in a system. So instead of adding more devices immediately, the team focused on refinement, signal timing, connection geometry, load symmetry, not to force results, but to listen to what the system responded to most naturally. And the response was clear. The cleaner the network became, the calmer it behaved. That calm was eerie. Energy systems don't usually get calmer under scrutiny. They get noisy. They expose flaws. They reveal margins. This one seemed to relax, as if disorder was the only thing that bothered it. By now, external pressure was building. Not public pressure, private. Invitations. Requests to observe. Requests to replicate. Requests framed very carefully, with words like evaluation and neutral oversight. Still no announcements. Because once replication begins, ownership dissolves. And yet, in a quiet lab, a decision was edging closer. Not about whether to scale, but about where. Because if this network could operate the way it was behaving, there were places where it would matter immediately. Remote locations. Isolated systems. Environments where failure is expensive and resilience isn't optional. And that's when someone finally said what had been circling the room for weeks. We should test this somewhere that doesn't forgive failure and doesn't benefit from hype. No one laughed, because everyone understood what that meant. It meant stepping out of controlled silence and into conditions that don't bend for theory or optimism. Where results aren't explained, they're lived with. And once that step is taken, there's no rewind button. The system doesn't just prove itself. It chooses sides. And as plans quietly formed around that idea, one truth became impossible to escape. The most dangerous phase of this experiment hadn't happened yet. Not because the questions have been answered, but because the stakes have finally caught up to the curiosity. What began as 10 silent devices linked in a room has evolved into a challenge that reaches far beyond any single lab, any single theory, or any single group of believers or skeptics. If the system holds up when exposed to the real world, it won't arrive with fanfare. It won't need to. Its impact would be felt quietly at first, where power is scarce, where reliability matters more than headlines, where failure costs more than disbelief. And if it doesn't hold up, then this experiment will still have served its purpose. Not as proof, but as a reminder that progress has never come from comfort. Every major leap began as an uncomfortable question that refused to go away. For now, the devices remain where they are. Connected. Monitored. Waiting. Not to convince the loudest voices online, but to meet reality on its own terms. Because in the end, technology doesn't need belief. It needs time.